Okay, let me see. There we go. Okay, so the contents are going to be the basic characteristics of grooving, achieving high efficiency machining. We're going to look at 2 case studies in the field, one of wide width grooving, expanding the width of the groove, also a case study of deep grooving, and lastly, looking at when and if to use special tooling when it comes to grooving. So most of the applications you're going to run into are O-rings, snap rings, seal rings. Sometimes you're grooving to relieve threads or grinding areas, lightweight items, gear cutting reliefs, oil grooves. The groove types that we mainly see, as you see up here, we're going to look at external grooving, internal grooving, and face grooving. Also, the different shapes that you encounter are when you do shallow grooving, like a GBA or something like that, when you widen a groove, or when you have to go deeper and make a deep groove. So normally to increase efficiency, the first thing we all look at is let's just increase the cutting speed, or the feed rate, cutting conditions. But you got to be careful, because in doing this you can incur different issues. So like in wide grooving, if you simply increase the cutting conditions, the chip control could be good, but your quality is going to drop and you're going to decrease your tool life. Same thing in shallow grooving. Just by increasing the specs, your quality is going to most of the time affect your surface finish and your tolerancing. And in deep grooving, just by increasing cutting speeds, things like that, your chip evacuation it gets bad, and so you start recutting chips and have bad chip evacuation. So we want to look at the following areas in order to fully realize and achieve the high efficiency by controlling everything. Of course, the cutting conditions, but you also got to look at chip control, molded chip breaker versus ground chip breakers based on what your finish requirements may be, the diameter of your parts you may be grooving. Also, in your tooling aspect, you got to make sure you got the proper setup, and you're also doing the correct process layout. In other words, make sure you're getting your cycle time down by looking for things in the process that you might find erroneous as to what the end user may be doing. So the first thing when we're looking at this, let's see how cutting speed affects your grooving efficiency. So again, you just simply want to increase cutting speed. Well, we're going to see how that affects it. Okay, so we're going to look at four different parameters. In this one, let me get back to the material. It's a 4137. We're using in this aspect, or this example, a GBA 43 MY chip breaker. So we're going to be looking at 4 different speeds. We're going to be looking at 160 SFM, 500 SFM, 800, and 1200 SFM. The feed rate's going to be the same on all 4 at 3 thousandths inches per rev, and we're going to a depth of 80 thousandths of an inch. So we're going to look at these, and I'll comment on it after you watch all 4 of these run. So that's a 160. Now we're going to do 500. Going to 800. And now 1200. Okay. So on all these, of course, you saw cycle time basically improving, of course, the faster we went, but let's look at what's actually happening with the the determinants of speeding up your cycle time. So if we look at the finish across the top of the chart at the different speeds here, okay, so at the lower speed, as we've discussed many times, your basically your surface finish is going to be out of whack. It's too slow and it's not creating good chip control, as you saw. Very unstable chips at the lower surface footage. But at 500, as we increase the speed, our surface finish basically maintained about the same all the way across. So you see we got good finish here from the 500, 800, and 1200. So you're thinking, oh, okay, well, we're just going 1200 then. Be careful. So at 500 and 800, you can see we're still stable at 500, good surface finish, nice chip. But at 800, we're still stable, a little bit more curly. But when we get up to the 1200, you can see it's very tangled, it's very unstable. So even though we can maintain a good finish because, you know, it's going to be nice and shiny and good, an RZ value, it's not going to provide us good chip control. So the speed is very important to pick the right speed for the application by not only looking at the finish, but look at the chip evacuation as well. So now if we look and see what the feed rate does to the scenario. So as you saw before, we were running at 3,000s per rev. So we're not going to go now. We're going to pick the middle of the road SFM at 500 where we had decent chip and good surface finish. But we're going to look at feed rate of 1,000s, 2,000s, 3,000s, and 5,000s per rev. We're doing the sidewall here. That's why we're saying the depth of cut, you can think of it as the width of cut, is going to be at 12 thousandths on this insert. Now, I mean on this part. So we're going to look at this and then we'll comment. So first at 1 thousandths per rev. Two thousandths. Now 3. And finally 5 thousandths per rev. Okay, so the results of this one now all across the board in the surface finish, they're going to be relatively the slower the slower the feed rate. Of course, we already know that's going to give you a better RZ value, as you can see here. So as we increase the finish, you know, or the feed rate, our finish is getting a little bit worse and worse. And then, but all across the board, we're still within the spec of the print. Okay, everything's good. But in this instance, you got to look at the chip evacuation. As we've learned, if your feed rate's too small, your chips are going to be harder to maintain, right? They're not thick enough. So 1,000's feed, good finish, bad chips. 2,000's feed, good finish, bad chips. When we get back to the 3,000's and and we're at 500 SFM, the 3,000's at the sidewall. Now we're able to basically curl the chips because we're getting a feed rate that's maintaining a thicker chip and able to break the chip. So very, very stable, as well as at the 5,000s per rev, nice stable chips. Now I will say you get better curls here, but at the 5,000s per rev, I believe that this is a very nice chip as well. So at this case, we can go with the higher feed rate. Now let's look at how the width of cut affects it. So we're running it at 500 SFM. We're sticking with 3,000 inches per rev. Now we're trying 3 different widths on the sidewall. We're going to go in depth of cut of 2 thousandths, 12 thousandths, 20 thousandths, and 31 thousandths. So let's look at this. 12, and then finally 31. Okay, so when looking at results of this, again, with the width of cut changing, it really doesn't have the effect on the surface finish, right? It actually gets more engaged of the wiper or of the radius, and so the finish is actually pretty consistent all the way across the board. However, at the lower feed rate, I'm sorry, the lower width of cut at 2000s, you can see we get nothing but a thin spirally chip. At 12 thousandths width of cut and 20 thousandths width of cut, we get stable chips. But what's going on here is the interesting thing about this is, keep in mind now, this is a 12 thousandths wide radius, right? So we're at the radius width with that MY chip breaker. So it's basically hitting the width of the radius, where here we're just rubbing against the outside of the radius. Here we're completely engaged to the radius width, and it's completely engaged in the running down the side of the chip breaker, where it actually has chip control from that MY because of the way it's positioned on the radius of the tool. Now, the reason these are still breaking, we've gone a little bit beyond the radius width, so we're more engaged into the MY breaker. It's doing a sidewall, so that's why we're still stable, but we're getting a little bit more of a funky chip here, but we still get nice breakage here. But if we get too far inside with the width of cut, we're not able to maintain good chip control, just one big long spiral. It's thicker than this spiral, but it's just one big long spiral. We're not going to have good chip control. We're going to have issues with this getting wrapped or scratching the part. So the key is maintain somewhere around the width of the radius when you're doing your sidewall in your width of cut offset. The other thing is, of course, you got to look at two different things here. We offer both molded chip breakers, and you just saw the MY work on that one. Now, this is a GBA example, and ground chip breakers in this type of insert, right? The features, of course, of the molded inserts, you're going to get good chip control. You're going to get nice tight curling because that's what the breaker's made to do. It's made to force that chip into the middle of the dots to make it curl better. The ground chip breaker, the downfall of this one is you really don't have chip control unless you're going to do some kind of dwell cycle, but you're always going to get a spirally chip coming out of that. So sometimes there's issues with it getting wrapped around your workpiece or your holder or scratching your part. But it does provide lower cutting forces, and it's going to offer, because it is a ground breaker, higher precision and tighter tolerances in situations where you need that. Finish is relatively going to be the same on either one. So now we're going to look at a case study that we looked at. It's wide grooving, so we got to open a groove by doing a series of plunges. And so we're looking at the customer's print to the left. We got a high wall here, 5.5 millimeters, got a low wall here, 1 millimeter less, 4.5. Got the corner radius, so we're going to have to basically come in and finish that. We're now looking at a 6 millimeter wide GMM with a 0.8 millimeter radius MW breaker. The problems they're having: chip control, too long of a cycle time, we're leaving a ring behind we got to get rid of, and the tool life is too short based on all the issues above. We're looking at a width of 800 thousandths and a depth of cut of 22 and 18 on the two different walls. So cycle time at this point, you can see here's the path: tool one, plunge, plunge, 3 plunge, 4 plunge. Come back, finish the wall radius here, tool 5 or pass 5, 6 come down, finish the wall and finish the floor. Okay, so the width now on the sidewall and the bottom portion, or the width of cut is now only 40 thousandths that we're removing in move number 5 and number 6. All has a feed rate of 6 thousandths per rev. Cycle time is currently 25 seconds, but you can see the chip evacuation issues that we're having. So let's look at this. First pass, first plunge, second plunge, third, 4, come back, finish the wall to the left, the long wall, leave 40 thousandths to finish, come across the floor, and as you can see, we're going to push that ring, and that's going to have to be removed in the final process. And not only do we have bad chip evacuation, but we also have the ring that's going to have to be taken off in a separate process. So before, here was the roughing pass, 1, 2, 3, 4, right? This is just the roughing passes we're looking at right here. We're going to evaluate this. Okay. So again, we saw the chips from that roughing pass. We got a machining time just to the roughing pass for 15 seconds. We're going to alter this pass. We're going to drop the 1 pass, and we're just going to do 3 plunges this time, but we're going to alter up the positioning. So we're going to do the first plunge to the left, second plunge to the right, and then third plunge in the middle. Okay, so now we improve the chip control and shorten the cycle time by 4 seconds by doing that. Now we're going to look at the finishing move, and the finishing move before, you remember, was pushing the ring over, and we'd have to get rid of that somehow. We're going to show you a different method for getting rid of the ring. So by doing it like this, there's no way to get around leaving a ring behind. So I'm going to explain this just for a second by changing the machining direction in the end. So now we're going to come over and we're going to do the long wall, but when we do this plunge, we're going to walk over just a little bit at an angle. Okay, we're going to bring the tool up at an angle, 15 degrees or so. Then we're going to come over, finish the short wall, and come across. Basically, when we get to the end of this slope here, there's nothing left to push away. So I'm going to let you watch this now. So leave a slight angle. Now when we come in, so as you can see, clear ring. You know, we went from 4 plunges to 3 plunges. So that meant we had to leave a little bit more on both sidewalls to finish up than doing the 4th plunge, but that's okay. There was no need to get that. We can easily handle that much with the cut when we finally do the plunge on the sidewall. And it also allows us two things: shorten the cycle time, 3 seconds. More importantly is, as you see, when you start doing your plunges, just simply 1, 2, 3, 4 like this, you're only cutting on one side of the insert, okay? The only time you're cutting on this side of the insert is when you're basically finishing and walking across the floor. So you always want to do your plunging offset. So 1, 2, and then in the middle 3. That way the tool is completely engaged every time it gets plunged, And so there's even wear across the nose, which is what you want to see. So to go back, so you don't want to ever do a 1, 2, 3, 4. Okay, that's only going to wear this side of the insert as you go across. Okay, by alternating on this way, 1, 2, and then 3, your insert is completely engaged in every single plunge, even in the center plunge. So, I mean, we leave a little bit more on the sides to finish up, but that's not an issue. So we're going to look at another problem here. This is another case study we documented for deep grooving. Problem with these processes is on the production line. Mainly, we got a bottleneck at tool number, the second process. So the problem with the second process is a longer cycle time, shorter tool life, and they're using 3 different holders in this operation. We need to have this at least the same as these, if not shorter, or else you're going to produce a bottleneck and you're going to have parts waiting. Okay. So this is the work piece. As you can see, we got a shallow groove, and then we got to come in here with a deeper groove for something. So this is the process they're currently using. They're using tool 1 to machine number 1 through 4. So 1 rough, 2 rough, 3 finish, 4 finish. Okay. Then they're coming in with tool number 2, and they're roughing out the deep groove with process 5 and 6. So plunge, plunge for the deep groove. And then they're coming in for tool number 3 and machining the finishing move of the deep groove, move 7 and move 8. So all in all, we're taking 34 seconds, 15 seconds, and 13 seconds. So you got to look at this scenario and figure out what would be the best way to shorten cycle time. Okay. It's tool 1, this is tool 2. It's going to rough out the deeper groove. And then finish. Cycle time 62 seconds. So here's the improvements that we came up with on this one. So we moved the second process roughing to the first process. So when the first process, as you saw on that bar chart of mine, they were just doing the OD and the ID face, taking 24 seconds to do that. We were just worried about the grooving process. I didn't touch on that, but that's there. That was process 1. Process 2, you just saw what happened. Rough, rough, finish. Come back with another tool. Rough, rough, another tool, finish. 62 seconds for the second process. So what we're going to do is we're going to rough everything at one time. So we're going to rough the shallow and the deep at one time. We're going to add it onto the first process after the OD and ID facing. And so we're basically adding an extra 14 seconds to the process by this roughing pass. Okay. So now we're going from 24 seconds to 38 seconds on the first process. So that's increasing that first process, but that's okay. The second process, we're now going down to 25 seconds by just coming in and finishing the entire groove, top and bottom, shallow groove and deep groove. So we're also going to be reducing the number of tool holders needed from 2 to 3 by doing this process. So now we're going to look at the new process here, the roughing and the finishing. The first is the roughing. And now the finishing move. Oh, and you can also see we're still getting unstable chip control. we're speeding up the process, okay? We're reducing the cycle time, but as you can see, there's still some chips we got to deal with. Now look, let's look at the finishing. Okay, so that was 25 seconds, but again, we still got some chip control issues. Yes, we're improving the cycle time, but we still got chip control issues. So we're halfway there, right? And well, I'll point this out in a minute. So if you'll notice before, we were having chip control issues even by pecking. So we still were pecking in that process or dwelling and still having chip control issues. So in that case, you want to look for our latest, greatest product. That's why we're always coming out with new chip breakers. So you're looking here, we're using the old GMM MW insert, right? Still having a peck and still having chip control issues. Now we're going to the KGD style, the GDM with the new GM chip breaker. It's not new now. This was back in the day with the GM chip breaker. But by doing this, now we can eliminate all the dwell cycles, and now we can increase this the roughing cycle because we're not having to peck from 25 seconds down to 14 seconds. All right, no dwell, reduced it by 11 seconds, and you see very stable chip control just by switching inserts to a different chip breaker. And now we'll look at the finish process again. No dwelling on this one, even in the other one, but you could still tell we were having chip control issues. But now by switching to the GDM with the GM breaker, stable even from the shouldering side. So half the battle can be cycle time reduction, but always pay attention to your chip control issues too, and always look for the chip breakers better for the job. So basically you can see now we reduced the bottleneck by 24 seconds from 62 to 25. We consolidated the holders. We went from 3 holders down to 2 holders. We improved the tool life because we're using a different tool for the roughing and the finishing instead of using the same tool for roughing and finishing. So we got longer tool life as well. So this is not a new KGD style system, but this is why we developed this system. But just keep in mind, you guys already know about the KGD features. I'm not going to go into this with the tool holder, the quick change blades. But the GM features, some of the features of the GM breaker is definitely for improved chip control. We made the instead of the dots, it basically forces the chip, squeezes it into a narrow channel, makes the chip narrow, easier to evacuate from the deeper grooves, stabilizes the chip evacuation direction, and it improves the chip control while shouldering and traversing with this section here. So as you can see, very good chip control with the GM chip breaker. And that's what we just proved even over our product in the last slide. And not going to end this long, let's so you guys know, we do have the GL breakers, lower feed, the general purpose GM, and also we have the higher feed GH breaker available as well. Low resistance, we got the ground breaker here called the GS. This is mainly, like it says here, for the non-ferrous stuff. We have the full nose radius for copying, the CM series, and then we have the PM strictly for the first choice for cutoff. So looking at increasing efficiency by going to special tools. So standard insert, if you had this groove right here, you would have to do a tool pass such as this. You'd have to do 3 tool pass or 3 passes, initial plunge, clean up here because we got 2 different radii, and we got the chamfer on the top end. You can see the chips by the grooving side and the chips by the chamfering side. So always look, is it valuable to just go in with a special insert made directly for the groove? Is it cost effective? Is it worth the investment to the end user? If so, it's always a better option to go with a special tool for something like this, as long as we can produce it and be cost effective at the same time. And this is just a case study of what you were looking at here. The special tool here, the purpose was to shorten the cycle time. So we were doing this tool here like you were looking at before, with just a regular GBA 43R 1.25 0.1 millimeter radius, cycle time 4.7 seconds. Again, it's just common sense. We go to the special breaker already with the chamfer on it. Of course, we can shorten the cycle time significantly, but we can also increase the tool life because the insert is always engaged in the cut fully as it plunges. So you can definitely increase tool life as well, because you're not having to do a roughing and a finishing move with the same tool. So finally, looking at at grooving efficiency, set up the appropriate cutting speeds, feed rates, and depth of cut. First of all, go to a molded chip breaker for chip control. Go to a ground chip breaker if you need lower resistance or smaller diameter tooling. When you're doing wide grooving, the techniques there are to shorten machining time by decreasing the tool pass when possible. Improve the chip control and tool life by changing traversing to grooving. And do the ring countermeasure we looked at by changing the machining direction at the end of the groove, like I showed you, by tapering up and then coming across. And there'll be no ring left behind. Deep grooving technique, shorten machining time by improving the processes. Increase efficiency by implementing new product offering, which that example is always find the better chip breaker, the better holder, jet coolant through, whatever we have to offer, that's going to increase your tool life and shorten your machining time. And also, when you can, special tools are always good. We do a lot of grooving tools back in the day when we had the lightning fast. I don't know, some of you guys might be old enough to remember that, but it was a special turnaround time on top-notch grooving. And when I was in production, that was one of the things we did. We did a lot of specialty grooving tools, and that really saves a lot in cycle time and also tool life as well. So I hope you guys got a little bit out of this today. Got any questions?
None came through.
Okay, and if not, you can always email. I'll try to get the quiz out tomorrow for you guys, give you plenty of time to get it back to me. Anyway, if there's no questions or you got some later, you think about something, email or call, and that's going to do it for today. And I appreciate you guys joining in. Talk to you soon.